Okay, so let's start back into the study guide where we left off. Accumulation functions and the fundamental theorem of calculus. We're on page 44, part of the way down the page, right after where we left off yesterday. So it's funny, there's not a lot here, but it's really, really important. And I think, again, as long as you remember to use units when you are working things out, when you're trying to come up with a solution for something, I think that's gonna go a long, long way. Oh, that's right, because their fundamental theorem of calculus is what I keep calling, and I'm sure I will forever call part 2. All right, so this is when you have g of x defined as an integral from a to x of some function. Typically, they'll give you the graph of f of t. And so if you want g of 5, start at whatever number a is and go to 5 and find your area of that function. You might go backwards. If you go backwards, just remember that when moving backwards, anything above the x-axis, its area would be negative, and anything below the x-axis, its area would be positive, again, because you're moving backwards, and it's like a double negative. Then there is the part that is designed to always save you a lot of time. If you're trying to find the derivative of this function, then it just means the derivative of the integral, and instead of finding an antiderivative and then finding the derivative of that, you can save time by, I always say plunk the a, substitute the x, substitute the x in for the t. Now also keep in mind that this might be a function of x, like it is right here. So if it's a function of x, you also need to multiply by the derivative of that function of x. So we take x squared, we plug it in for t, so that's right there, and then we multiply by the derivative of x squared, which is 2x. Why is that? Well, we're really doing that here also, but the derivative of x is 1, so we don't need to think about the times 1. All right, and if you need to look up anything else, I would look up Fundamental Theorem of Calculus, Part 2. All right, so antiderivatives in the Fundamental Theorem of Calculus. So remember that, just be comfortable with your notation, going back and forth. Like this one says, if g prime of x equals f of x, then the antiderivative of f of x is the antiderivative of f of x is g prime of x. So let me scroll down and find something that's a little more helpful, because, yeah. So this is what we want to start to look at, is right here. So when you have two numerical bounds, right, we don't have a function of x this time, then our little in-between step is we usually find the antiderivative of little f of x, which we'll call big F of x, and we'll go from a to b. And then by the fundamental theorem of calculus, you have then capital F of b minus capital F of a. All right, so that I don't think you need a ton of review for. But you might, and don't forget your plus c, right? Especially when we're solving differential equations, don't forget your plus c. Basic antiderivative rules, if you have not studied those yet, study them, and not on Sunday, okay? Study them before Sunday. Sunday, you should already know all your stuff. So the antiderivative of x to the n is x to the n plus 1 over n plus 1, and so on. These are all formulas with x, which are great, but on your formula sheet, you have them with u's. And that reminds you and helps you kind of a little bit for u substitution. So I would definitely kind of memorize my formulas probably from the u sheet. Now, speaking of substitution, here we go. It might be beneficial to understand the way that this is written. But really, I think it's just all in the applications right now. And we can look at this example and see how it helps you to understand the way this is written up here. But you have, hopefully it's obvious to you guys now that this is an e to the u, right? So to integrate, what you want to be thinking of is the e to the u, its integral is e to the u plus c. And then that means that x cubed must be your u. So then if u equals x cubed, then du equals 3x squared dx, and we see x squared dx right here. So x squared dx equals 1/3 du, because we can divide both sides by 3. So then we have this, right? And then its integral is 1/3 e to the u plus c, and then plug your stuff back in for u. So that's our little reminder of your u substitution. Oh, now how these go together is, what's the easiest way to show you? So this is f prime of g of x, g prime of x. What I like to concentrate on here is this g of x is going to be your u, and what we need to be present in the problem somewhere is the derivative part, right? So whatever we decide to be our u, our g of x, the derivative of it has to be in here. Now, with the exception of maybe the numbers or the coefficients that would go with it, because we can always adjust coefficients by division. But in other words, since there's an x cubed here, there had to have been an x squared somewhere in the problem for us to be able to do this by u substitution. All right. So here's another example, and what's interesting about this one is you actually have a choice as to how you want to solve this. Oh, no, never mind. I was thinking that when that was smaller, I was thinking it said sine of theta, cosine theta. But because that's sine theta, then definitely, because this is being raised to a power, that has to be your u. And then your du would be cosine theta d theta. Now, if that exponent wasn't there, can you see how we could have had u equals cosine theta, and then du would equal negative sine theta d theta, right? Which would just, again, we can always adjust things with constants by division or coefficients by division. But because this was raised to a power, then yeah, this was definitely going to be a u squared du. And then this is worth mentioning right now. Notice that they changed their bounds from 1 to 0. You guys might not necessarily change your bounds from 1 to 0 if you had to finish this problem. You could continue on and say, okay, that's u cubed over 3, and I still don't know what my bounds are, but I could put the sine of x, remember this was from before, I could put the sine of x back in for my u, so I could say sine cubed of theta over 3, and then I could go from pi halves to pi. But if some, and that's fine, if you're going to finish out the problem, you're more than welcome to do this. Sine of pi is 0, sine of pi halves is 1, so this whole thing ends up being like 0 minus 1/3 or negative 1/3. You can do this by plugging the original stuff back in, your x stuff or your theta stuff. But if they just give you the rewrite of a problem for your multiple choice, you do want to make sure you understand how to change your bounds, right? So how do I change my bounds? Well, if u equals sine theta, then when theta is a half, u equals sine, did I say a half? Pi halves. When, then u equals sine pi halves, and sine pi halves is 1. So that's why that's a 1. Now if I want to change the pi, well, if theta is pi, then u equals sine pi, and sine of pi is 0. So that's why that's a 0. And yes, absolutely, these things could be going in like in a backwards direction. Pi halves to pi flows this way, but 1 to 0 flows backwards. And I mean, that's fine, right? Because you know that, again, I think we discussed this in class, the area under this curve, sine squared theta, cosine theta, is not going to be anywhere near the same as what the curve looks like if it's just y equals x squared. So, I mean, your bounds can be anything to, they could go in any direction to account for that and to still have the same area. All right, other integration techniques. Oh, this is so important. I could see them having, one of these for you to worry about. When the degree of the numerator is greater than or equal to the degree of the denominator, there is no amount of u substitution that's going to help you. Okay, so what we're going to have to do is divide. And what we did in class was I kind of went over doing like a long division thing, and you could do whatever kind of division you want. Let me get rid of the stuff on the page. So I don't know, I was just comfortable going x minus 1 into x cubed plus x. Now, I guess, I don't know, maybe I might be feeling a little synthetic division. I don't know. You could also, as long as the bottom is linear, you can do your synthetic division where if you let x minus 1 equals 0, then you'd see x equals 1. That's called your root. And your root goes in the box, and then your coefficients, 1 for x cubed, 0 for x squared, 1 for x, 0 for the constant. So we can do long division or we can do synthetic division. So what I do is I bring this down, right? And then I multiply this times this, put it here, and then I add. And then I multiply this times this, which is 1, and I put it here, and I add. And I multiply this times this, and I put it here, and I add. All right, I'm going to show you if we did long division instead, you know, how to treat this answer, and basically how to rewrite this integral. So x times what gives me x cubed? Pause if you want, or mute me and try to do this yourself. Okay, so x squared, and then if I multiply, I get x, I get x cubed if I multiply x squared through this. X cubed minus x squared. Now I'm going to subtract this whole thing, which is going to make that go away, and it's going to make this a positive x squared. Now I'm going to bring down my x. Notice I spaced these out so I didn't end up with things aligned that weren't the same exponent. Okay, x times x, positive x, would give me x squared. Now I'm going to distribute the x through. X squared minus x. And now when I subtract these, I get, what do I get? 2x. And so finally, I get x times what gives me 2x? That's a 2. So 2x minus 2, and when I subtract, I get a 2. So I'm really looking at the same answers here because these give me my coefficients of the one less degree term. All right, so whichever way you choose to do this, you end up seeing that this integral equals the integral of the quotient plus the remainder over the divisor. You know, just like if you took 7 divided by 4, that goes into there once, subtract, and it's 1 3/4, right? 1 3/4. We're just writing this with a little plus sign. 1 and 2 over x minus 1. Okay? Finally, you can integrate this using the power rule. The first part's a nice one, right? We have x cubed over 3, then we have x squared over 2, then we have 2x, and then over here, our Usubstitution is x minus 1, du equals dx. These are the kind of U-subs that I say you can kind of do in your head to save the time because you don't have to worry about any coefficients. So this is really, you're integrating 2 over u, which is 2 times the natural log of u. So we're just going to go plus 2 times the natural log of, and then we're going to plug that back in. And then finally we have our plus c. Okay, so if you want to read through their example, if it makes any more sense, you can, but yeah. And then don't forget, there's also properties of logs where they could, you know, kind of hide this. You might see this term as a plus ln x minus 1 squared. I dropped the absolute values because once I square something, it's always positive. And how did I get squared? I brought this coefficient in as a power, you know, so you could have all of that stuff plus this. Yeah, so be careful when you get answers with logs. All right, so I see that my time is getting close to 14.5 minutes, so I'm going to stop this video and start another one for the next part.